Circular motion. Well, if you recall from your math analysis class or the trig class, the circular motion deals with many circles, I guess, right? And in part of a circle, the components that make up a circle is the most important one is the radius. And the distance that radius sweeps out, right, is called the arc length. And the angle that it sweeps out, we represent that with theta. When it sweeps out a one complete revolution, right, we call that arc length circumference. And when it sweeps out one complete revolution, that theta happens to be tau, right? And tau happens to be 2 pi. So they decide to divide that one complete circular sweep as equally, I guess, part, called it degrees, and there are 360 degrees in one complete circle. Well, the discovery of pi. If you were to actually draw a circle and measure out the circumference, okay, with a piece of string, we would be doing this in a lab actually, and divide it by its radius. Okay, so no matter how big the circle is, or small the circle is, or the medium-sized circle, if you measure out the circle circumference with a piece of string, and then divide that circumference by the length of the radius, you would always get this magical number, 6.283, blah, 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 blah. Okay? Well, the ratio, they called it radiance. And the radiance really is a fictitious unit because if you think about it, the arc length is a measure of length, and if we were to use meters, arc length would have unit of meters. And since radius is also length, it would also have unit of meters. So if you were to look at this, these units should cancel each other out, giving you nothing. But these ancient Greeks decide to give this fictitious unit called radiance because it is a special ratio of arc length divided by radius. All right? And in a pi radians, right, there are 3.1415 radians, right? And pi radians is also equal to 180 degrees. It's a half a circle. So we could all go from degrees into radians and radians into degrees by multiplying by its factor of 1, pi radians over 180 degrees, right? Or 180 degrees over pi radians should give you the conversion factor. All right, so this should be reviewed, so I'm not going to go too much more deep into that. All right, the important questions. In what instantaneous direction, right, does a particle moving in a circular trajectory move? Now, if we were to assume that this satellite is orbiting around the Earth in a circular orbit, and let's say it is going in a clockwise direction. Okay, this is going in clockwise direction. Well, we know from the previous lesson that all objects will travel, right, in a tangential to the path or the trajectory, right? The velocity vector shows you the direction of motion. Therefore, if it's moving at a constant speed, okay, the velocity vector will always be pointing towards tangent to the path of a circular trajectory. So here, right, this would be the direction of the motion, and the motion's direction is indicated by the velocity vector, okay? And it is tangent to the circular path. Similarly, at here, of course, we'll also have, right? I forgot how long this was. This is 2 centimeters. Yeah. All right. So this will also have, right, velocity vector that is tangent to the circular path. And if it's going at a constant speed, the magnitude of that instantaneous velocity will be tangent, and it would remain the same length, right? And then here, let's say, it would also be tangential to the circular path, and then here would be the direction of the motion, like so, all right? So if it's going at a constant speed, the magnitude would stay the same. But notice my velocity is changing because the direction of my velocity vector is changing, okay? So for the instantaneous direction, right, you have to really take a look at the velocity vector, okay? Okay? And the direction of the velocity is tangent to the trajectory, right? Okay? So if the satellite is moving with constant speed, okay? It's moving with constant speed, which means uniform circular motion. Is it accelerating? Right? Is it accelerating? Well, velocity has two components. It has magnitude and it has direction. Well, you can change velocity by changing the magnitude, definitely. So you could slow down or speed up. And when you do that, you're changing the magnitude of the velocity. Therefore, you are changing velocity. And when you have change in velocity, you have acceleration. Well, since velocity also has direction, you can change direction, just direction by itself, and you can also change velocity that way. And since by definition, if there is change in velocity, there is definitely change, there's an acceleration happening, right? So when you change direction of the velocity, acceleration must be present, right? That's non-negotiable, all right? So since All right. So since velocity vector is changing direction, there is change in velocity. Therefore, there must be acceleration. Okay? Non-negotiable. There has to be acceleration. Well, what's the direction of acceleration then? There must be some direction for acceleration because acceleration is also a vector, right? Well, let's say we were watching something going in a circular path, okay? And it's going in a clockwise direction, like the satellite that we were watching. And let's say we're looking at this thing so that I'm going to try to be as accurate as possible. This looks like oh my God, look, what the hell is all this, right? So I'm going to redraw this so if you could follow me, okay? So for now, just ignore this for now and follow what I'm going to be doing. So hopefully that would explain things much better, okay? Now I'm going to do my best to make it accurate as possible so you could see it. So I'm going to use my protractor to really measure this thing out so that you can see the direction of acceleration. Oh wow, look at that, that's perfect. I didn't realize that. I can use this exact same one. So I'm going to take a look at like 20 degrees from this side to 20 degrees from this side, okay? So I'm going to look at two time frames, time instances, where if this thing is going in a circle, I'm going to look at this point right here as my initial starting point, just right, the TI, and this right here is my TF, final time. So here's my initial, here's my final. So even though it's continuously going in a circle, I'm just looking at these two time intervals, okay? And look at their instantaneous velocity at that moment, okay? So if I were to look at instantaneous velocity at that moment, if you think about it, okay, it has to be tangential to the path. So to be tangential to the path, it has to be perpendicular to the radius, okay? So you don't have to do this at home, but I'm just going to try to do my best to make it look so accurate that you could see it better. So here, this is rough drawing of my velocity vector, instantaneous velocity vector at ti. So I'm going to make the magnitude of this to be 3 centimeters. That looks a little longer than 3, sorry. So I'm going to try to make it 3 centimeters long. And that's my V initial, tangential to the path. Okay, so if I were to look at the radius and then look at that, and then basically what you'll see is this is like the 90 degrees right here, right? And then here again, if I were to look at the moment, so here, so my radius is that, right? And then if I were to look at my tangential, right, so it's going to be like this. And then if I were to draw my instantaneous velocity vector at VF, right? Here's my VF. Here's my VF. All right. So notice because it is going at a constant speed, my magnitude of my VI and VF should be exactly the same. Okay. So again, this should be perpendicular to my radius because it is a tangential to the circular path. So here, this again is 90 degrees. Now, since the direction has changed, there has to be change in velocity. All right. So if I were to look at the average change between these two time frames, I'm going to draw the actual change in velocity right at the center because it's average. All right. So from here, I'm going to have my delta V. So look at this. Here's my VF. Since my change in velocity is equal to VF plus negative VI, right? Because that's the subtraction of vectors is adding the negative vector, right? I will draw my final velocity here first. So I'm going to basically take my final velocity and place it right here between these two time frames, right? So here, I'm going to do my final velocity first, and I'm going to draw 3 centimeters, exact same length, right? So here's my final velocity. I just transfer the final velocity to here. Okay, so here's my VF. And I'm going to add my negative VI. So here's my VI. If I slide it down and then flip the arrow, I get my negative VI. So here, I'm going to try to draw it as parallel as possible. So see, this is parallel with my ruler, and I'm going to draw 3 centimeters of, right, 3 centimeters in that direction. So here is my tip, and so here's my negative VI. Right? That's my negative VI. So I am subtracting my negative VI, well, VI from my VF. Therefore, my resultant is my delta V. Here is my resultant right here. This is my delta V. Okay? So, delta T obviously is T final minus the T initial. Right? If I divide this delta V by delta T, my acceleration vector is really nothing more than, right, delta V over delta T. So this delta V and acceleration direction has to be the same. And depending on what your delta T is, your delta T will determine the magnitude of your acceleration. If your delta T is less than 1 second, then your acceleration will be bigger than your delta V. And if your delta T is more than 1 second, then your acceleration will have smaller magnitude than your delta V. That's all it is. So the direction of my acceleration is along my delta V direction, okay, which is pointing towards the center of the circle. Okay? So let's write that down. So So it doesn't really matter which two time frames I look at in this motion. I could be looking at two time frames from here to here, or 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 even like here to tiny bit here, right? It doesn't really matter which two time frames I look at. When I draw this change in velocity vector, it will always point towards the center of the circle as long as it's going at a constant speed. Okay? Well, how can I get the magnitude of that acceleration? Well, the magnitude of the acceleration is a little bit more complex, but it's not that hard. If we were to take a look at this triangle right here, VF, VI, and delta V, and if we take a look at this R, R, and L, okay? So I'm going to try to redraw that. I'm going to try to re-represent it here. Let's see. Of course, I had to draw it up here, so I run out of space. Sorry. So if I were to look at R, R, and L is the secant line from the tip of R to tip of R. And this is the angle theta. And in this, when theta is small, and when I say small, I mean like less than 10 degrees, right? 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 Then the arc length, the dotted line is the arc length S, right? Then arc length S is pretty much congruent to L. Okay, so this arc length and this L are pretty much indistinguishable. Then, if I take a look at this right here, this V vectors, right? Here's my V, I guess you could say my VF, and here's my VI, right? And here's my delta V. This angle here is same theta. Okay, you can see that happening if you were to look at this proof. It's pretty much the same angle if you were to follow these two parallel lines. Okay, where if you were to look at that, this is the right angle right here, and this angle is basically complementary angle of this angle phi, right? Because this is also right angle. Well, this angle is exactly same as this angle because of corresponding angles from geometry class. So you don't have to learn how to prove it, but this corresponding angle from this and this are the same, which is same angle theta right here. All right, now, because these are similar triangles, okay, because these are similar triangles, the proportionality has to be the same, okay? So you can say S or L, basically, they're same things, right? So S over R has to be same as right delta V over V. Okay? So if I bring this V to the other side, okay? If I bring this V to the other side, I have V times right, S over R. And that is equal to delta V. If I divide both sides by delta T, I'm not really changing the equation here, right? Because I'm multiplying by 1. Well, this right here, S over delta T, is V. That's the distance divided by time. So I would have V times V over R is equal to this delta V over delta T, we know it as acceleration. Therefore, that acceleration that we just talked about has magnitude of V squared over R. This acceleration, we're going to call that radial acceleration because it follows the radial direction of our circle. Okay? So the magnitude of my radial acceleration can be calculated as the speed of this object going in a circular motion squared divided by its radius. So we proved it now. Now you can use it. Okay? Boom. The direction of this radial acceleration, we just calculated it right here. The direction of a radial is always inward towards the center of the circle. Okay? So all circular motion is definitely an accelerated motion. This is very, very important. Even at constant speed. Okay? All right. You have a question? Kate, you have a question?
Yeah, so do the initial velocity and the final velocity have to be like equal to each other?
Only the magnitude. Yes, only the magnitude. The direction is obviously,
Okay.
yeah, the direction is obviously the different, right? But the magnitude, the speed wise, they're exactly the same speed, right?
Okay, because I was gonna ask if they didn't have to be, then how would you know which V to use? But that makes sense.
Yeah, but it doesn't really matter because the magnitude will be the same, right? Good, good. You got it. All right. Any other questions? All right. All right. So now let's take a look at the difference between radio acceleration and similar radio acceleration, but one is going to be going into the circle, another one's going to be going out of the circle. And that depends on who's observing what and what's happening to the observer. I know it sounds kind of weird, but there's two different radio accelerations. One is, right, centripetal acceleration, and other is centrifugal acceleration. Now, I know you guys in the chemistry class, you use centrifuge, which would actually put the material inside a test tube and you put it in the centrifuge and you spin it at a really high RPM to make the settlement of the particles into the bottom of the test tube. And the heavier object will settle down further down the lowest point of the test tube, and then lighter one will float to the top. Right? That's called centrifuge. Right? Now, the centrifuge basically means center fleeing. So the particle is basically trying to flee away from the center. All right. Now, centri, from Latin derivative of centrum, not a vitamin, by the way, but right, it's basically means the middle point of a circle or the center of the circle, right? And petal, from the Latin peto, to seek or strive after. So centripetal is center seeking, where fugal, from Latin fugito, to flee or to fly from, right? Avoid or shun, means this centrifugal one means center fleeing. Okay. Okay, center fleeing. So, how is that different? Well, we know that circular motion will produce an acceleration in a radial direction. So it means it's going to be along the radius, right? However, imagine yourself holding onto a rope, right? And your friend, this is your friend, and this turtle is you, right? Your friend, you, right? Some friend. Huh? Now, your friend is spinning you around in a circular motion, and you're holding on to that rope, right, with your dear life. And as you are being spun around, you, the observer, if you are the observer being spun around, you would definitely feel you are fleeing from the center, right? You are definitely going to feel that you are fleeing from the center. Well, let's say I put you in a bubble now, right? And you are inside that bubble, and your friend is again spinning the bubble with you inside. You would feel that you are getting pushed against the side of the wall of the bubble, and you are feeling that you're going to be fleeing away from that center of the circle. Because you, the observer, right? You are the observer, will feel being pushed out. So the center fleeing acceleration is only true for the observer who is being spun around. But anyone who's observing this system away from the system, right, will only see a centripetal force this way, right, when it's observed away from the system. Okay? So when you have an accelerated frame of reference, right? This accelerated frame of reference is non-inertial frame of reference. So okay, in non-inertial frame of reference, you would get these phantom forces coming out of nowhere that cannot be explained, right? Because if you are inside this bubble and this bubble is completely pitch black, dark, right? And you're being spun around, you'll feel this like just a push against the wall that cannot be explained. Like, why am I getting pushed against the wall? You know? And that cannot be explained if you're inside that bubble. But we all know by if you're observing outside of a bubble, we can see why this is happening. But if you're inside that bubble, you cannot explain that. All right? So in non-inertial frame of reference, right, there will be phantom forces that cannot be explained. So we will not be working in non-inertial frame of reference. All right? So spinning turtles, right? So the turtle will feel an outward centrifugal acceleration inside of the bubble because this bubble would be accelerating, right? And it is non-inertial frame of reference. We will never spin turtles in bubble or try to solve problems inside of spinning objects. Okay? Every problem that we're going to be doing in Newtonian mechanics is going to be inertial frame of reference. Okay? So I know somebody's going to ask me like, well, but Mr. Kim, aren't we like on Earth? Hopefully that's not flat. That's going to be spinning. And when isn't Earth going around the sun, right? Instead of big chariot of Apollo carrying the ball of fire across the sky, right? So aren't we technically in non-inertial frame of reference? So all Newtonian mechanics should be thrown out the window? Technically, yes. However, if you actually calculate that acceleration, it's so minute that it's negligible. So we can treat all the things happening on the surface of the Earth as inertial frame of reference. All right? The acceleration is like negligible. So we're okay. So we're not in a bubble being spun around. All right? Even though we are. Any questions? All right. All right. All right. So, moving on. So people feel like centrifugal confusion is happening because they're putting themselves into that, frame of reference as an observer. That's why everything gets all messed up. But you have to keep yourself as an observer away from the system and observing it from outside. Don't put yourself in there in that bubble spinning it around. All right? So here in the situation below, a particle 1 is spinning in a circle of radius r when the string attaching him to a circle breaks. So it's going around, 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 and then breaks. Which path does he follow as he flies off the circular orbit? So we're looking at this like, like bird's eye view of an object or a bubble going in a circle, I guess, right? Or a person going in a circle. If we break the string off right here, remember what vector determines the direction of motion? All right, shout it out. Come on, what vector?
The one tangent.
Tangential, absolutely, right? Very good. So velocity vector will determine the direction of motion. So when this string breaks, which way is this person going to go? Kate, what would you say?
The way that is like pointing where the tangential one is.
Absolutely. So which is it, A, B, or C? Ben? Yeah. Tangential. That's the velocity vector. So as soon as this thing snaps, this person's going that way. Tangential, right? For those of you, who went to Sunday school, I mean, David and Goliath's story, right? David, who's a shepherd, had this weapon called a sling. And sling is made up of a leather strap, and there's a pouch at the end of that leather strap. Right? There's a pouch. And at the other end of the pouch, there was another leather strap. Don't try this at home, okay? Now, you would tie this one side of the leather strap onto your finger or your wrist, and the other strap, you hold it in your hand, right? Then, you would place a nice round river rock inside this pouch. You whirl this thing around in a circular motion, right? You whirl it around in a circular motion. And then you release this strap that you're holding in your hand at a right moment. And this rock will come out of that pouch tangentially, roughly around 120 to 160 miles per hour, depending on who's doing it. If you get hit by a fastball of 95 miles per hour from a major league player, it's going to do some damage. But if you get hit by 125 miles per hour of a solid rock, it'll do some real damage, right? And Goliath can tell you that, right? Well, Goliath didn't die because he got hit by this. I was there. I saw the whole thing, right? Goliath got hit by this rock right between the forehead, like right between the eye and the forehead, and he just lost his consciousness. Right? I was there. I'm telling you. And when he fell down because he lost his consciousness, David calmly walked up to Goliath, took out his sword, not David's sword. David didn't have a sword. Goliath's sword, and chopped his head off. And he became the king of the Israelites. Wow. Well, physics, right? Physics. So don't try this at home. You're going to be making a lot of windows broken. All right. So this is the path you'll be taking. All right. All righty. All right. I'm going to get the circular motion out of the way today. And then we'll do some homework problems. And then we'll go over some homework problems if you have any questions. So lesson 5, period of motion and frequency of motion. All right. How do we find the speed of an object going in a circle? Right? I mean, by definition, speed is really nothing more than v, which is the distance divided by time. Right? That's what the definition of speed is. Right? The distance that object travels when it's going in a circle is really nothing more than just circumference. Right? And the circumference divided by the time it takes to make one revolution. Right? Would be the speed of an object going in a circle. All right? Well, how do we measure this time to make one complete revolution? Well, if I had to do it in class or like lab situation, I would not try to take a look at this and say, here's your R, and then like make a reference point and go, and then like trying to do a stopwatch. It'd be almost impossible, right? Because you're not that accurate with your reflexes. So to measure the time for the one complete revolution, I would like time like maybe like 20 revolutions and then divide that time that it took to make 20 revolutions and then divide it by 20 to get time for one revolution. I think you'll have much more accuracy that way. All right? So time to take 20 revolutions, right? And then you divide that by 20 to get time for one complete revolution, right? We call that period. And period is represented with capital T. Okay? And period basically is time to complete one revolution. Okay? And don't get that confused with regular t, lowercase t. Capital T is different. All right? So to get time for one complete revolution, I would just measure like 20 revolution, if it's going at a constant speed, that is, right? And then divide that by whatever the revolution that you did, right? Then you'll get yourself time for one complete revolution. So let's say we know an object makes 4 revolutions in 20 seconds or 2 seconds. Right? With this information given, we can find the frequency of each revolution. Now, frequency pretty much represents, right, number of revolution, right, in 1 second. Okay? So the frequency of this object going 4 revolutions in 2 seconds is 2 revolutions per second. Okay? The time needs to complete one revolution, therefore, is, we called it a period already, is just half a second. Right? So period and frequency are reciprocal of each other, right? So the period is 1 over frequency, and frequency is 1 over period. So the period of this particular example happens to be 1/2. This is wrong. This is wrong. This is actually 1/2 seconds per revolution. Okay, 1/2 seconds per revolution. So, period and frequency, reciprocal relationship. So, how far does an object move in one revolution? Well, the distance that object travels in one revolution is called the circumference, right? So the distance is known as 2 pi r, right? Per revolution, right? So if I want to find out exactly how fast it's traveling, all I have to do is find the speed of that, and that's distance divided by time. So the distance divided by time is simply 2 pi r over the period. Or it can be 2 pi r f. So there are two ways to figure out, right? So velocity or speed can be found by, right, 2 pi r over the period t, or it can also be calculated by 2 pi r f. They're all same things. So if we were to substitute this v for the v squared over r for the acceleration, we can also calculate now interpolated acceleration by this. A sub c means acentripetal, okay? This is same as a radial, okay? This is right? Centripetal acceleration, which is center-seeking acceleration, or same thing as radial acceleration, which is v squared over r. And since v is 2 pi r over the period t, okay, you can simply plug this in and square it, which would be 4 pi squared r squared over the period squared divided by r. And this r and r squared would cancel out, leaving you 1 r at the top. So AC can be represented as 2 pi and 4 pi squared r over the period squared. Okay. Or I guess you can also represent that as, right, 4 pi squared r f squared if you want. Right. You don't have to memorize this. You could always derive it later on if you know this. Okay. All right. All right. All right. Well, in real world, things don't always go nice and smoothly at a constant speed, right? Somehow it had to get there. So you start from zero and then you speed up, speed up, speed up, speed up, and then you reach that certain speed and stay at that speed. What happens between zero to that constant speed? It had to be spinning faster and faster and faster. Well, then you have non-uniform circular motion. Okay? Non-uniform circular motion is when object is going in a circular motion, but it's not going at a constant speed. Okay? So when things are going at a non-uniform circular motion, right, the object is either speeding up or it could be slowing down. Right? while spinning in a circle. Okay? So when things are speeding up or slowing down while going in a circular motion, we have non-uniform circular motion. Okay? In that case, not only we have a circular motion, which means it has circular or radial acceleration, it is speeding up or slowing down, so the magnitude changes. Therefore, we have now linear acceleration. This linear acceleration is the change in velocity of the magnitude, and radial acceleration is change in velocity of the direction. So we have both accelerations happening simultaneously when we have non-uniform circular motion. Okay? That linear acceleration is caused by the tangential acceleration because the velocity vector is pointing tangentially, right? So the tangential acceleration is the linear acceleration. And the radial acceleration or centripetal acceleration is happening because the velocity vector is changing its direction. All right? So a radial, we already know how to calculate the magnitude of that, right? So a radial is basically a sub c, and that is v squared over r. Right? A tangential is acceleration that we already know, and that is the change in speed over change in time. Direction obviously is going to be all messed up, so we're only working with the magnitude of the speed or the velocity here. All right? In most cases, right, this acceleration will be constant acceleration, right? So if it's not, right, right, then it will be a very jerky motion. And what do I mean by that? Well, I'm not trying to be funny here. This is actually a mathematical term, okay? When we have a position function and when we take a derivative of that position function, we know we get velocity function. We know that from the summer assignment as well as from your calculus class, right? Then if we take a derivative of that velocity function, we know it's going to be an acceleration function, right? So if you think about it, right, r of t is position function, right? And then r prime of t is really the velocity function. And then if we take a derivative of that, which is the second derivative of the position function, which is first derivative of the velocity function, is the acceleration function. And that is basically the acceleration. And then the third derivative of that position function is the second derivative of the velocity function, which is the first derivative of the acceleration function, is jerk. Okay? And then snap, crackle, pop, right? Rice Krispies. Well, all right. So it won't be a very smooth accelerating motion when you have non-constant acceleration. It'll be a very jerky motion. Okay. So here, my tangential acceleration is obviously tangent to the circular trajectory. And since this is going in a circle, I have radial acceleration happening simultaneously. This v for my radial acceleration, since the speed is changing, this v has to be the instantaneous speed at this time or at this moment. Okay? So okay, it has to be that instantaneous speed at that exact moment. Okay? So when I combine these two, right? So if I add a tangential, right, plus a radial, I get my total acceleration like so. So this is the total acceleration of my two accelerations. And because this is tangential and this is radial, this angle has to be perpendicular and it has to be 90 degrees. So we have a right triangle. Therefore, the magnitude of my A total is equal to the square root of, you know what it is, right? So A tangential squared plus A radial squared, right? Direction would have to be standard direction, right? So in this particular case, this would be the beta, right? And then, since this is pointing in the third quadrant, right? So beta is equal to, right, tan inverse of, right? So this is beta. And beta would be tan inverse of, right? Opposite, right? In this case, this is the opposite right here. So it's not always going to be this case. It's going to be slightly different depending on how it is, right? Divide that by a tangential in this case. Then because this is in third quadrant, my theta happens to be, right, 180 plus beta, right, absolute value of your beta. So this is a special case. In this case, looking at just this one, okay? This will change depending on where it is and which part of the circle it is. If it's here, it's going to be different. If it's here, it's going to be different. So make sure you understand that this is a special case, right? Just for this example, right? Okay. So let's take a look at an example problem. Let's take a look at an example problem. Here we have an example problem of non-uniform circular motion. A particle, right, moves clockwise, and so it's moving this way, right, in a circle of radius of 1 meter. It starts at rest, so my initial speed, right, so what color should I use? Okay, V initial, right, is 0. So this is the initial starting condition. And we don't know how fast it's going at V final. That's same as VB, okay? And this is VA, right? But it's traveling in a semicircle here. So this S, the distance S, right? So distance S, which is just pi r, which is just pi meters because r is 1 meter. Its speed increases at a constant rate. So when the speed increases at a constant rate of 1.6 meters per second squared, we know that this is a tangential. Okay? Now let's answer some questions. How long does it take to travel halfway around the circle? Well, it starts here and it travels s distance, right? And ends up here. It starts from rest and it has acceleration of this. So we can say, okay, well, we know V initial is equal to 0. We also know the distance, right? Delta x, or I'm going to say S, because we're not going in a straight axis, but the distance it travels, right, is pi meters, right? We know the acceleration, linear acceleration, tangential acceleration of 1.6 meters per second squared. And I'm looking for time to go from A to B, right? So they were looking for time to go from A to B. Well, it looks like we have 4 variables listed here, and we have 3 known and 1 unknown. That looks like equation number 2 from your summer assignment, and that is, right, delta x is equal to VIT plus 1/2 AT squared. Delta x, which is same as S, is just pi, is equal to, initial velocity is 0, so this whole term drops out, plus 1/2 times A tangential, which is 1.6 times T squared. So if I solve for T, my T now is equal to square root of 2 pi over 1.6. And that comes out to 1.98 seconds. Now they ask us, okay, what is the speed at point B? Well, speed at point B we're looking for v at point B, which is basically VF, right? We know VI, which is point A, which is VI, which is 0. We know A, which is 1.6 meters per second squared. We know time to go from A to B now to be 1.98 seconds. So we have all the 4 variables listed here with one unknown, right? So we can use the first equation, equation number 1, which is VF is equal to VI plus AT. So VF is equal to 0 plus 1.6 times 1.98. So my VF comes out to 3.17 meters per second. This is the speed at V at point B. Okay? So what is the direction of the velocity at B? So if I were to look at this, right, circular motion, at point B, the velocity vector is going to have to point tangentially, and it's going to be pointing this way because it's going clockwise. So that is the velocity at B. The direction is basically the negative y direction. Or if you want to show off, you could say my velocity vector at point B is equal to 3.17, right, meters per second in the negative y hat direction. All right? Negative y hat direction. D. What is the centripetal or the radial acceleration at B? Well, the radial acceleration will be in towards the center, right? That's my AC, right? Well, the magnitude of AC is equal to, right, at B, right, is V at B squared divided by R. Therefore, V at B happens to be 3.17 meters per second. Square that, divide by 1 meter. That comes out to 10.05, right, meters per second squared. That is the magnitude of my AC. Therefore, my acceleration, radial acceleration at B, right, at point B is equal to, since it's pointing in the left, I'm going to say negative 10.05 meters per second squared x hat as my centripetal acceleration at point B. Well, what is the tangential or linear acceleration at B? Well, that's given to us in our problem. A tangential is really nothing more than 1.6 meters per second squared. That was easy. But the direction, right, of a tangential will always be right tangential to the circular path. That simple. So if I were to look at this, right? Here's my A tangential. So this is the circular motion, right? And here's my A tangential at that point B, right? And then you know it has to be down like this, right? So you can say A tangential is equal to, right, negative 1.6 meters per second squared y hat. So we know this is A tangential. And we know this is a radial, right? So this has to be A total. So A total is equal to, right, A tangential plus A radial. Therefore, the magnitude of that A total is equal to square root of, right, 1.6 squared plus 10.05 squared, right? So the magnitude of A total is equal to 10.18 meters per second squared. Now, this beta right here, right? This beta is equal to tan inverse of opposite, which is A tangential. Now notice how this is different than the other previous example problem, over A radial. So my beta comes out to tan inverse of, right, 1.6, and this negative 1.6 because it's in third quadrant, over negative 10.05. So my beta comes out to 9 degrees. So my theta, the direction, has to be 189 degrees. All right? Your homework will be up to and including page 15 in your homework packet. Okay? Up to and including page 15 in your homework packet. So you have the whole weekend to do this. All right? Umar?
How did you know that beta was in the third quadrant?
Look at the way it's pointing. If it's pointing this way, it's first quadrant. If it's pointing this way, it's in second quadrant. If it's pointing this way, it's third quadrant. If it's pointing this way, it's fourth quadrant. So think of this as the origin. This is the origin. Does that make sense? Wherever this is or you're looking at is the origin. And it's pointing in the third quadrant. Kate, you have a question?
Yeah, so for when you were looking at the, in like C and D, when you were looking at the direction,
Yeah.
what would happen if it wasn't like,
It'd be a lot more difficult, yeah. Like if it's here,
like if it wasn't just one direction, if it was like some X hat and some Y
yeah,
hat?
absolutely. Correct. Correct. But you would have to know more information about that though, you know what I mean?
Yeah.
Like you would have to know what angle it's swept out and all that. Then you should still be able to do it. It's not hard, but that's a great question. I'm glad you asked. All right. Any other questions? All right, outstanding. I'll stop the lecture here. Oh, are we over 2 minutes? Sorry. All right. I'll let you guys go 2 minutes early next time.